All right. We don't need my iPad. All right, bet. Can everybody see that?
Yes, sir.
Bet. All right. So this is the first day of chemistry. So let me ask by show of hands. Let me look at the participants list. By show of hands, how many of you have had chemistry already, like high school chemistry? One see one hand. So some of this is going to be redundant, but that's okay. Redundancy in science is good because the more you hear something, the better it's going to stick. Okay, great. All right. So obviously we're going to start out with this in this first section, really basic, a lot of definitions. And we're going to start out just giving you an idea about how chemistry is all around us, which really, that's what made me fall in love with chemistry, is the fact that, you know, when I realized how ubiquitous it was, like everything involves chemistry. And so we're going to talk about that. We're also going to talk about phases of matter. So let me put the date here, a different pen. Yellow. All right, so this is the 10th. Can't believe it's 2022. All right, so we're going to talk about phases of matter. Right, and we're going to talk about physical and chemical properties. And this is basically the overview for this entire section. So each one of these sections obviously has subtopics that we'll discuss. So physical and chemical properties. All right. And then of course we got to talk about measurements. We're going to be doing a lot of calculations, so we need to talk about sig figs and how to convert between units and things like that. And then we're also going to talk about some mathematical treatments of measurement results. All right, so mathematical treatment of measurements. All right, so those are the four major topics, and within each topic we'll have subtopics that we'll discuss. That the first couple of lectures are going to be a lot of definitions and a lot of things like that. Not a whole lot of chemistry per se, but just really laying the foundation so that we can understand what we're talking about going forward. So could somebody define chemistry for me? Anybody? What is chemistry study? What is it? Especially if you had it before. That's why I asked that question. So what is chemistry? What are we studying?
The study of matter and the changes it undergoes.
Yes, so we're studying matter. All right. And matter can be anything that what has mass and occupies space, right? So we're studying matter, we're studying the composition of matter, right? The properties of matter. And the interactions of matter. So those are the changes that matter undergoes when it interacts with other types of matter. Right, so matter's composition, matter's property, the properties of matter, and the interactions of matter. That's what chemistry is the study of. All right, and when we talk about matter, we know that matter is anything that has as you learned in high school, more than likely. Has mass and they occupy space. That's what matter is. So it can be anything. So let me ask this question. How many of you have ever seen, well, actually, let me pull it up since I have my screen share. How many of you have ever seen the Egyptian art? Let me just pull up a pharaoh. I'm just going to pull up the image. How many of you have seen this image before of an Egyptian pharaoh? Excuse my Wi-Fi is really slow.
I have.
All right. What do you notice about that image?
It's very symmetrical.
It's symmetrical. Okay. It's made out of metal. All right. Notice the eyes are colored. There's also some, let me see if I can pull up this whole image so I can zoom on it. Oh, go ahead and mute your microphones unless you're answering the question. All right, so it's made out of metal. Notice that you got all these different colors in here too, right? Red, blue, blue going around like the lines here. So what you'll notice is, go ahead and mute your mic.
Oh.
All right, what you'll notice is these colors, they didn't just come out of nowhere, right? Somebody had to actually study that to determine what composition and what compounds had to be added together in order to get a color like that. You had your hand up, Caleb? Or is that from when I asked earlier about who's taking chemistry? All right. So those dyes that are used to make that blue color, that's chemistry. People have been studying chemistry and how to convert matter into other forms for millennia, right? The color in the eyes, you see it's different, it's dark, it's black, not like the same blue. So that had to be composed, right? Somebody had to come up with a way to take some element or some compounds that were known and convert them into something that could be applied, right? And really, when you're talking about converting matter, matter is either gonna undergo physical changes or chemical changes. So this is just to, and the metal, the gold itself, right? That had to be melted, and it had to be fashioned, and it had to be at a certain temperature because gold has a specific melting point. So all of that is tied up in chemistry. And really, when people started studying chemistry was really when they were able to control fire, right? So being able to control fire meant that you could control temperature. You can melt things at certain points. You could cook food, right? You could, even cooking is chemistry. Have you ever noticed, let me ask this question, and we're not taking a whole lot of notes right now, so it's just a warm up, just kind of an icebreaker, but have you ever noticed, how do you know when something is done when you're cooking it? Let's say you're cooking a piece of chicken in the oven and you seasoned it, and even the seasonings are chemistry. But how do you know when it's done? Like, how can you tell if those of you who cook and cook often? Because I have a method that I use to know when something is done. And it's a very simple method. Anybody, you can unmute and answer that question. How do you know when your food is done? If you're baking a chicken breast in the oven, or you're cooking.
The color of it, or like you can cut it open, like you can look in the inside and see the color.
Okay. What about the smell?
Yeah, the smell will be enhanced as well. So
to me, well, that's how I know when my food is done. If I'm cooking it in the oven, that's how I know when it's done, because you can smell the aroma. Because what happens is when you start cooking it, there are compounds and molecules and things in that food that get converted into other stuff as you cook it. And so when you can smell it, that means that there's a chemical change that is taking place. So everywhere you look, no matter where you look, you're going to be able to find some link or connection to chemistry, right? Excuse me. So let me pull this back up. So what can we say about, my iPad is really acting stupid, sorry. What can we say about chemistry? It's everywhere, right? When you think about dyes, think about the clothes that you have on, the materials and the fabrics that your clothes are made of. When you think about your cell phone and the materials that is made, that those cell phones are made of. You think about all of these things, right? Medicines, different medications, all of these things involve chemistry. So you see chemistry every day, even in your body. When you eat, right, that food gets digested. That's a chemical process. Enzymes and acids act on the food to break it down and release the nutrients to your body. So all of that is chemistry. And anytime matter is manipulated, right, we could say that chemistry has taken place. So let's write that down. Let me put that in here. So chemistry takes place. Matter is manipulated. All right. And not in a physical sense, but in a sense of converting it to another type of matter or some or like that. All right. Any questions? Can anybody give me an example of some chemical process that's happening even right now around you, besides what's happening in your body? For those of you who've had breakfast, and that breakfast is making its way through your intestines and being broken down, and energy and sugars are being released, so you can actually, function. Somebody give me an example of chemistry that's happening around you right now.
My food in the refrigerator being cold.
Okay, your food is being kept, right?
You're right.
It's being maintained so that the bacteria or whatever don't take it over and make it inedible. What about your computer screen or your phone screen that you're looking at right now? What do you think that display is made of? That LCD display or that LED display? All of that is a result of some chemical process happening. So it's ubiquitous. You can't get away from it. If you have on socks or underwear, the band that's holding that underwear up or holding your socks up, that's that band is a result of some chemical process used to make that material, nylon or spandex or whatever. So it's everywhere. So we're going to keep talking about that. And let's talk now, kind of shift gears a little bit and talk about the scientific method, because a lot of what we see as chemistry didn't just pop out of nowhere. Like a lot of the stuff that we know because someone has conducted enough experimentation to develop a theory or a law to say, when I do this, this happens. And it happens every single time I do it, and it rarely deviates. But that's not a haphazard method of determining that. We use the scientific method in order to do that. Right? And so with the scientific method, we use experimentation and we use observation. So you run an experiment, you observe the results, and based on those results, you either continue to innovate on whatever you're doing, or you go back to the drawing board. So this is based on experimentation and observation. Very important, right? And you can think about this in terms of even now, and I'm not trying to, this is not a debate, this is just an observation. Even now with the rancor and the argument over the vaccine, what's in it, what's this, what's that, there's a lot of back and forth, but really what's going to prove to be most beneficial in the end is, have I applied a method to what I'm saying, in order to prove or disprove my point, right? So that's why the scientific method is very important. And there is it's called a method for a reason, because it's a systematic way of thinking about an observation, right? So what's the first step? Anybody? What's the first thing that you think a scientist does before they develop some new process or some new reaction or whatever? Or what do you think an ancient Egyptian alchemist did prior to finding out that if I mix this and this, something is going to happen?
Define the issue.
So you have a problem or a issue that you want to solve. That's correct. And then you think about a way to solve it. What is that called? When I come up with a tentative way to explain what this issue is or what I've observed.
A hypothesis?
A hypothesis, right? So the first step in that scientific method is to develop a hypothesis, right? That's your tentative explanation of what you've observed, right? That's your, we used to say an educated guess, but it's a little bit more than a guess because it's based on some observation, right? You say, let's say you look at, I have a jar of honey right here on my countertop, and I'm looking at that and I'm wondering, what makes it so sticky? That's my observation. Honey is very sticky. I wonder what makes it so sticky. And then I run after my hypothesis. That's when I need to do some experimentation, right? That's when I need to test my hypothesis. So the second step in that scientific method is to do experiments, right? That's what an experiment is. It's testing of an idea. So I'm testing my hypothesis, and based on my experimental observations, I can develop what's called a law, right? So you have a hypothesis, and hypotheses are tested, and you look at the behavior of whatever you're testing, and then if you get results that continue to show you the same thing, those results can become a law. So a law is a summary of experimental observation. And again, it's a lot of definitions. Right. One of the laws that we will talk about is the law of conservation of matter. Right. The way that law was developed was basically through experimentation. What was observed is that anytime you take matter and try to convert it into another type of matter, or you take matter and convert it into something else, the masses stay the same. And so because the mass stays the same, that means that no matter was lost in the process. So that's how the law of the conservation of matter was developed, because every time you do an experiment where you're converting matter from one type to another, the mass of that you started with and the mass that you end with, if it's in a closed system, is going to be identical. So that means that I didn't lose any matter in that process. All right. So a law is a group of experimental observations. So we know that the law of conservation of matter was developed because of multiple experiments that gave you this exact same outcome. All right. So you test your hypothesis, and from those tests, you develop laws, and you can also develop theories, right? A theory is an explanation for an observation that is reproducible, right? Well substantiated. What that means, when I say well substantiated, I mean there are volumes of work that contribute to the fact that this is what I see when I do this, right? This is what I observe when I apply this particular method to this set of compounds or this set of chemicals, right? So this is, it's well substantiated. And I want to deviate here because I like to make stuff current and make it make sense in real time. When you watch a YouTube video that is supposedly scientific, if there's no, and I'm just saying this as a old scientist, always ask for the evidence. If somebody just gets on and starts talking about something without evidence, then it's really best to take that with a grain of salt. Because if it's not well substantiated, if you don't have evidence to back up what you're saying, the best thing to do is to keep testing whatever you're saying until you either develop the evidence or you have to comment back and say, it's not what I thought, right? That's how science works. So theories are well substantiated. They are testable, right? And they explain natural phenomena, right? So they explain natural phenomena. So let me pull up a diagram. I want to pull up two diagrams because I want to show you, first of all, how chemistry is everywhere, which is right here. Can you see that? A lot of times you hear chemistry referred to as the central science. Let me move this down. Right, you hear chemistry referred to as the central science. This is why. Because every discipline or sub-discipline in STEM, with the exception of mathematics, even though mathematics is connected to chemistry because we use math to determine and explain chemical phenomena, right? You can see the overlap, right? Chemistry is related to everything. It's related to biology, it's related to medicine, it's related to geochemistry, physics, because the physics helps us to explain the chemical phenomena as well. Like physics, you know, dealing with, when we talk about matter interacting, it interacts when different elements collide with one another and they either bond or they don't bond, or they bond in a specific way, or electrons are knocked out. All of that is a consequence of a physical interaction, but it might be an interaction that we can't see, right? So chemistry overlaps with all of these different areas, especially material science, which connects to chemical engineering. I'm not sure how many of you are Chem majors, but material science and chemical engineering go hand in hand, because when you think about materials that, you know, if you notice, like, I don't know how, whether you remember, you probably don't, but that was a time when a Teflon coated pan was a big deal, right? A pan that did these non-stick pans that you have now, they don't use Teflon anymore. They use some other coating, but back in when I was your age, it was all about Teflon, this fluorinated polymer that they could coat pans with, and eggs won't stick, and, you know, nothing will stick to it, right? But that's a material science issue. But the actual compound, the polymer itself, Teflon, comes from a chemical process called polymerization, where you take a fluorinated monomer and you shine light on it and you make a fluorinated polymer, and that polymer acts as your coating. So that's material science. But then the chemical engineering part comes when you have to scale that reaction up to coat 1 million pans versus only having to have a lab experiment where you have this coating and you can test its properties. So there are, you know, many layers of connectivity between chemistry and other disciplines. All right, any questions so far? So let me show you another diagram here with this. And again, this will all be on Blackboard, and we'll discuss it. But now let me show you this diagram with the scientific method, right? So first, you observe. Oh, I wonder what happens if I do this. This is what I think is going to happen when I do this, right? When I mix sodium and chlorine. I wonder what's going to happen. I wonder if it, if I have to heat it, can I just mix them at room temperature? Can I just leave them? I believe at room temperature, if I just put a block of sodium in a vat of chlorine gas, I'm going to get something different. That's the hypothesis, right? So you observe, you form your hypothesis, and then you experiment. Because from the experimentation, that's where you observe the behavior of the matter that you're trying to interact. You following? So you experiment, and then if your results are consistent with what your hypothesis is, right? Then it contributes to what's already known. That's how science works. If I have a hypothesis and I'm able to test it and prove that it is, correct or functional, then I publish that and I tell everybody about it. I tell everybody how wonderful I am, and I contribute to the overall body of chemical knowledge or scientific knowledge. If my hypothesis does not, if I can't prove it, if I have a hypothesis, but the experiments that I do don't prove it, then I got to go back to the drawing board and do more tests, more experiments, right? And if at some point my hypothesis is disproven, I can publish that too, right? Because that's also going to contribute to the body of knowledge in some form, even if it's saying what doesn't happen, right? So I contribute to the body of knowledge. If I do more and more and more and more tests and I get these consistent observations, then boom, I can say that this is a law, right? And then if I do additional testing and everything that I do lines up with what I hypothesized, then that's how it becomes a theory to explain a particular observation. All right. So this diagram, again, I'm going to post these notes to Blackboard so you'll have access to this. And if you have a question, feel free to unmute and ask it. If not, we're going to move on to the next topic. Any questions? No questions. All right. Everybody all right so far? Let me know if I'm going too fast or I'm not going fast enough or whatever. I need to move this. All right. So now we're going to talk about how chemistry is studied, right? Because it can be studied in multiple domains. It can be studied in the macroscopic domain. It can be studied in the microscopic domain, or it can also be studied in the symbolic domain. And we're going to talk about all of that. So let me paste this here right quick, because we're going to use that diagram in a second. But now we're going to talk about how chemistry is studied. And anytime you have a question, just unmute and ask it. This is more, I prefer this to be more of a discussion and less like me just, bombarding you with information. So don't hesitate. If you have a question, please interrupt and say something. I'm not one of those teachers that feels like, I'm the god of chemistry and you can't interrupt me while I'm talking. So please, if you have a question, just ask it, unmute and ask it.
I have
Go ahead.
So just to make sure, like there's 3 steps of the scientific method, or just to finish that note?
Well, yeah, so we have basically there are 3 steps, right? You have an observation.
Mm-hmm.
You come up with an idea as to why you think that observation is what it is. That's your hypothesis. And then you perform experiments in order to either prove or disprove your hypothesis. So yes, those are your 3 steps. Observe, make a assumption about what you observed and why it's happening, and then do the experiments to prove what you said is true.
Okay, thank you.
And sometimes, again, I mean, but see, here's the thing about science that people tend to overlook. Just because you do an experiment or you do some research is not always going to prove your hypothesis right. Sometimes you're going to be wrong, and that's okay, right? But then what it does is when you're wrong, you're able to modify your experiments or do different experiments to find out why you see what you see. So that's what research is all about. That's what science is all about. It's not like, oh, I said something, but I don't know what I'm talking about because this didn't match. No, I had an idea of what I saw. I had an idea of what I thought happened, but the experiments that I did just didn't bear that out, right? So I can modify my experiments. I can change my approach. I can do a different set of experiments to test this hypothesis. So that's what it's, I mean, that's why people are still doing chemistry in 2022, 2,500 years after people initially started studying chemistry. That's why we still do research. That's why papers are still being published in journals, every day, because people are always observing and asking questions and forming hypotheses. And sometimes your hypothesis may be based on some current, technology that's already out. Maybe you read a paper and saw something and there was a gap in what they studied. You say, well, what if I did this? Then you take that and you go and do your own experiments based on what's already known. So sometimes it's based on what's known. Sometimes it's based on developing an idea about something you observe that may not be known. But the 3 steps are to observe, to hypothesize, and to experiment, right? And the experiments have to be designed to answer the question that your hypothesis brings up. Great question, by the way. All right, so let's talk about how chemistry is studied. And basically, it's studied in 3 domains. And you've probably heard these before, right? The macroscopic, the microscopic. Fix that. Oh. Sometimes my brain is moving faster than my hand. So I apologize for that. When I get excited about a topic, it just happens. So macroscopic, microscopic, and then the symbolic. Right? So in the macroscopic realm, can you tell me what this prefix macro refers to? Or do you have an idea of what it refers to? Anybody?
Large enough for the eye to see.
Something large enough for very good. Something large enough for the eye to see. So it's visible to the naked eye. And tangible. So you can see it, you can touch it. That's what it means to study something in the macro realm. All right. And then in the micro realm, on the microscopic level, that's exactly what it sounds like. It's invisible to the naked eye. And again, there's a lot of definitions here. So you can expect on the first exam, it's gonna be a lot of definitions. All right. So on the microscopic level, it's invisible to the naked eye. All right. Sometimes there may be something that you can't see at all. So you have to conceptualize it. That doesn't mean that it's not real. It just means that you can't see it. So you have to come up with a way to describe it.
Can you describe what conceptualize means?
Sure. So let's say you have 2 atoms, right? 2 carbons, and there's a bond between them, a covalent bond. We're going to talk about covalent and ionic bonds later, right? There's really not a definitive way to see that bond, but there's ways to describe it, right? Because that bond happens between those 2 atoms, the covalent bond happens between two atoms when the orbitals that contain the electrons from those at the valence electrons overlap, when those orbitals overlap. So really, we can think about this as two orbitals on a carbon atom overlapping and sharing a pair of electrons. But we can't see that with the naked eye. We can only develop an idea as far as what it looks like or how it looks like based on what we know about orbitals and what we know about their shapes and what we know about, you know, the way they interact and overlap with one another. So that's what it means to conceptualize something. It's like you have an idea of what it should look like, but you can't really see it. So it's basically, you have to come up with a way to describe it, right? It's kind of almost like if you feel a certain way about something. I'm moving away from chemistry, but just trying to make it real, you know, like reality. Like it's almost like if I feel a certain way, but I can't describe it. So I say, you know, I felt a tingling in my toes. Well, I didn't really feel a tingling in my toes. It just, that's the way that I felt at the time. You understand what I'm saying? So it's more of a way to
Yeah.
describe something that can't be seen.
Okay.
Right. So in some cases we can see on the micro level, right? We don't have to conceptualize what a cell looks like. We can look at a cell in the microscope and see that it has a certain shape. It's got a cell. That's why when you study biology, you know all the parts, the mitochondria, the cell wall, all the plasma, all this stuff that makes up a cell. We know that because we can observe it, even though it's on a microscopic level. And there are some really, let me tell you something, there are some really, really powerful tools that are at our disposal as scientists to be able to see things on the micro level that are not visible to the naked eye. There are some really powerful tools that are at our disposal. All right. But sometimes if it's on a micro level, we may have to only be able to conceptualize it, only to come up with an idea of what we think it looks like to describe it. All right. And that's a great question, by the way. You ask any questions, right? It doesn't matter. Some of the micro level things that we can think about that are not visible, but we have to have an idea of what they look like. Think about subatomic particles. We haven't talked about atoms yet, but we can introduce it here, right? An atom is basically, I'm gonna use the Bohr model because that's the easiest thing to think about. It's a nucleus that has, I'm gonna color this in red and I'll color the neutron in blue. So let's say the nucleus has protons and neutrons. So the red is a proton. And then the blue is a neutron. Oh, ran out of space, hold up. So the blue is a neutron. And then around that nucleus, right, there's an electron that's orbiting that nucleus, right? So this is, and then this is the model that was developed even before anybody knew what an atom looked like, right? And it's still like, this is something that's invisible to the naked eye, but we have a concept. It's conceptualized. This is what it looks like. The nucleus has protons and neutrons, and then orbiting that nucleus, you have electrons, right? So those subatomic particles, we haven't seen those. We don't know like what an electron looks like. We don't know what a proton or a neutron looks like, but we have an idea because we've conceptualized it. Does that make sense?
Yes.
Mm-hmm. So when we study chemistry, we basically study it in three domains. We study it on the macro level, on the micro level, and then on the symbolic level, because we have to have a language, right? We have to have a way of describing what we're talking about. So this is the language of chemistry. Right? That's the language of chemistry, the different symbols, the formulas, the graphs, the calculations, all of that is what we call a part of the symbolic level of or the symbolic study of chemistry. So like when you see Na, right, on the periodic table, it's not Na, right? That's the symbol for sodium. So that's again, we have to have a language. We have to have a way to describe what we're talking about, what we're studying. So when we see Na, we know that that's sodium. When we see C on the periodic table, we know that that is carbon. When we see CO2, this is a symbol for carbon dioxide.
Huh?
On the lab report where it says which of the following recommended transportation accommodations are mismatched.
Mm-hmm.
All right. So these are symbolic, right? And so I have a diagram here that kind of deals with that. And then this is actually where we're going to stop. And then we'll pick up on Wednesday, talking about this again. Talking about this, just walking down this first chapter and these first set of concepts so we can have a good foundation going forward. So in the example right here, right, you have liquid H2O, right? You have solid H2O in the form of ice. And then you also have gaseous H2O. This is macro. All of these are macro. We see the solid, the liquid, and the gas, but we can visibly see them. We know that clouds are not solid, right? They're made of air, gas, like the gas that's in the atmosphere, as well as some liquid or vapor particles that are in the atmosphere as well, right? So but it's macro. I can see it, I can touch it. If I get up high enough, if I'm I can fly through a cloud. If it's low enough and I'm in some helicopter or what, not an airplane, obviously, because that's pressurized. You don't want to open the door. But if you are hang gliding, if you're skydiving, if you're in a helicopter and you pass through a cloud, you can actually touch it and see it. So all of these are what we call macro, right? These are macro depictions or macro manifestations of water, gas, solid, and liquid. But what we don't know and can't see is how the atoms are actually arranged. So that means that is what we call the micro, right? In the gas phase, you can see that the water molecules are very far apart. And also you can actually see what a water molecule looks like. The white atoms, let me zoom in on that. The white atoms are hydrogen. Let me change pens. So the white atoms here, hydrogen. And then the red atom is oxygen, right? This is on the micro level. I can't see this with the naked eye, but I know it exists, right? And then look at the distance between the molecules. So this H2O is what we call a molecule of water, right? It's a compound. It has more than one element and they're arranged in a certain way. So we call it a molecule. It's a molecule of water. That molecule, if you look at the distance between the molecules, right, it's pretty far apart. That's what differentiates a gas from a solid and a liquid. One of the things that differentiates it is the distance between the particles, right? Then if you look at the solid, that's also on a micro level. What do you notice? What changed? Anybody, just unmute and speak out.
They're more structured.
More structured,
Stuck.
right?
Yeah, like stuck together.
They're lined up. Is that right? Do you see the alignment is different?
Right. Yeah.
They're more order. Is that right? Everything
Yes.
is more orderly. So for this solid, you can see that this is more orderly, right? There's a specific alignment and it's going to be more, that's going to make it more rigid. That's why solids are solids. because of the way that the particles that, or the molecules or atoms that make up that solid are compacted. That's what makes it a solid. That's why it's so rigid. The other thing that you can't see on the macro level that's happening on the micro level is the velocity of those particles. For a gas, those particles are moving very rapidly. For a solid, they're moving very slowly, right? That's why, and a great way to think about that is ice, right? When you have liquid water and you drop the temperature, it slows down. First it decreases the energy, and then it slows down the movement of those particles. So that's why they come together like they do and they solidify, right? So when you're going from water, liquid water to ice, the particles are slowing down, right? But you can see that for the solid is more orderly, particles are more rigid, they're more structured, boom, you get a solid. And then in a liquid, notice how the order is different, right? It's still orderly, but the molecules are not aligned the same way. But you can't see that with the naked eye. You can only see that really by conceptualizing it and thinking about how atoms interact. And you base that, the way you conceptualize it is based on what's already known. You don't just pull it out of thin air, right? You base it on what you already know, right? That's why laws and theories matter. And that's why the experimentation that goes into developing a law or a theory matters. You can't just pull stuff out of thin air and start pontificating on it and think it's scientific. That's not how this works. And I say all that to say that we are inundated now with pseudoscientists on YouTube telling you everything about everything you eat and this and that without much scientific evidence behind what they're talking about. So test it, ask questions. Hey, why is this happening? I'm not knocking them. I'm saying ask questions. How do you know this? What experiments did you do? And if they can't tell you what they did to develop that body of knowledge or point you to a source, then take it with a grain of salt. And then obviously with the liquid, you can see that this is arranged differently. And we know that the difference in liquid and solid is that the liquid is more fluid. So we want to talk about the states of matter and all that stuff a little bit later. And then symbolically, this is how we express this, right? We have H2O, but in parentheses, we have an L to indicate on the symbolic level that this is water as a liquid, right? And we also have atoms bonded together. That's also a symbolic representation. So you see macro, micro, and symbolic all at the same time. So we're going to stop here. Are there any questions before we stop about anything?
When is our first test?
My plan is to do the first test. Our first meeting was Friday. So not this Friday, but the following Friday. So every 2 weeks.
Okay.
Yeah. So here's the thing. If we do a test every 2 weeks, that means that it's a lot less information. There's going to be a lot less information on that exam, right? But it's going to be fresh when we get to it, because if there's only a gap of 2 weeks in between when we take tests, you should be like ready to take the test, boom, because we've been talking about it. You've been studying a little bit every day. So when you get to the exam, it's cake, right? It's just a matter of applying what you know. So that's my plan, is to do one every 2 weeks. And we'll
I'm so sorry, go ahead.
Yeah, I will take some quizzes in between and things like that, but my plan is to do an exam like every 2 weeks.
So just to make sure, our first exam will be on the 21st.
That's the plan, yes.
Okay.
Mm-hmm. All right. Any other questions? All right. I think this is a good first start, a good jumping off point. And I'll see y'all again, God willing, on Wednesday. And we're just gonna keep pushing. If you don't have a book, I posted a link to a free ebook. It's called Chemistry 2E, 2nd edition. Please get it and start reading through that first chapter.